a bit of a late edition. Sam's been introduced. My name's John Barnes. I'm the technical manager at Engine-Soft. I want to talk to you about the smart digital twin. Now, what I mean by that, the digital twin, ICM Live. Smart, that's a combination of two things. Yes, one AI, the other one is optimization. Optimization can have elements of AI, but not entirely always the case. And we're going to look at it and try and work out how we can use that smart process to really speed up what we're doing with the digital twin and ICM Live. So I'll just go through just a bit of background, share with you what we see as being the challenge of doing live simulation, what our solution looks like, and then Sam's going to present really a case study that we've done in the industry, and I'll wrap up with some highlights. So the background itself, Engine-Soft, we've been in the water industry probably over 10 years. We were playing around with ICM sort of back end before there was ICM Exchange, linking it through Excel spreadsheets. And we've been broadly trying to help the industry work smarter, so by using these optimization and artificial intelligence techniques. And now we're getting onto this sort of second generation, doing it with a digital twin with ICM Live. So we've been working with Innovyze for some time, really trying to take that technology to the next level. The work that we're presenting here has also been on the back of some work with AECOM. They have some customers with this particular problem that we're addressing, and we went away and sourced out some way in which we could use artificial intelligence to sort out the issues they were facing with live simulation for their customers. And then ourselves, Engine-Soft, what we bring to the table is that we have a software package called Mode Frontier that does optimization. We can do that for drainage, and we can do it for clean water, so we can do for both of those things. And that's the combination of everything that we present today. So the challenge of what we see with live simulation, before we talk about the challenge, just really some of the great successes that it has created. Okay, that we can take some weather prediction, some tidal flood prediction. We can pass that information into ICM Live, into the digital twin, to have a simulation model, to have all of our assets talking to each other and the information from the real world. Be able to run some simulations and then say whether or not there's going to be an issue in terms of flooding that's going to occur. That can pass off some information to an operator. And that operator can then go and do something about that potential problem. Now, what I just want to say here is that is actually ahead of many manufacturing companies that we work with. Even in the automotive and the aeronautics, they can struggle to do this kind of thing, typically because they don't have the sensor information. They have the artificial intelligence, they just can't get their hands on the data. Where the water industry is you have your hands on the data, and now you're trying to get the artificial intelligence linked up. So the water industry is ripe for this kind of work. But there is a slight issue in what the operator does. Okay, he gets a signal saying there's going to be an issue. What does he do? Does he go on past experience? Where does he get his source of information from? So typically, there would have to be some kind of step, go back to modeling. Are they going to be the ones doing the modeling? No, maybe somebody else is going to be doing the modeling. And that can become time consuming, and you've only got a few hours because of the prediction of the weather is only running in cycles of a few hours, 3 hours, 6 hours, and you've got to get the answer back quickly. So what we're doing is looking at ways of providing that solution far quicker than just traditional simulation. So there's a limited time window, iterations can be slow, people may have to resort to low fidelity models just to get the runtime quick enough. And at the end of the day, you may not even capture the knowledge. So can you capture that knowledge back in for storms that will happen in the future? So here's the question: can we provide a real-time solution in the short term and still learn for future events? And that's what Sam's just going to present now.
Yep, okay. So I'm going to go through to begin with the sort of solution that we propose to the problem that John has just outlined. and run through, to begin with, what our view of the current digital twin with ICM Live is, what we're looking at here, and where we can sort of bolt on our neural network to that problem. So to begin with, we're starting with some inputs from our infrastructure. We've got our weather and tidal data or any other data that we might be inputting into our ICM Live model. We can come round, we transfer that data, and then we're starting to link up our physical infrastructure with our ICM Live model itself. So we've got that data, it's going into our ICM Live model. We're going round, we can format that data with data loaders and the other processes that ICM Live runs, and we can come around, analyze that data further, and then we're running our simulation however regularly that might be. So once we've got our data from our infrastructure, we've run around, we've simulated it, we can have a look at our floods and spills and either email the warning saying there is a problem here, we need to do something about that, or not, in which case no action needs to be taken. So our operator receives our warning that there needs to be action taken, and we start coming back around to the infrastructure. We could do something like adjusting the pumps, something along that sort of lines, and apply that to our network and respond to that weather data and tidal data with the understanding that we have. So that's all well and good, but what we were looking at was sort of how we best recommend what the operator should do, how we adjust those pumps in the most sensible way for the issue that we're seeing. So we're going to start off by having a look at our email warning and whether we can add more to that, whether we can make some sort of recommendation as to what the best way to go about that is using our artificial intelligence. So if we go around this little loop here, we can run some additional simulations in the background, get some learning from those simulations, analyze that data, and start gaining an understanding of that. So we could run lots and lots of ICM runs once we know about our weather data, but we run into much the same problem we were talking about before, that's going to take a period of time. We go, what if we try this? That simulation takes a period of time to run. Okay, that doesn't work. What if we try this? Okay, we need to have that learning already integrated and a sort of real-time solution to that. So we're applying our neural network in the top right corner. So what we can start by looking at is this is a real-time solution. So our neural network will already know about our network. It will have an understanding of what it is that we're trying to accomplish. And we can go around our neural network. So we've got our weather data that we initially talked about. And we can immediately move towards recommending a solution for our operator to move towards. And we can develop learning as we go around as well, as we run more and more models to train our neural network, but I'll go into that in a little more detail as we get further in. So this is our sort of real-time solution, the amount of time it would take to ask our neural network what the best solution is to our set of weather data is fairly minimal. It's essentially real-time, significantly faster than an typical ICM Live model would take to run. So we can go back round, as I was saying, we've got our problem that we've got emailed to our operator to begin with, and we're using our neural network, we can move towards emailing what a proposed solution would be to that problem and run around and we can tell our operator, okay, this is our proposed solution, and that can then be implemented. So we've got this slower learning cycle as well down in the bottom here. So this is sort of developing our neural network's understanding of what's going on within our network and running ICM multiple times to go through, develop an understanding of how the network responds to various inputs and train our neural network. So we have a same loop here, where we go around and we can run multiple ICM models in the background using Mode Frontier, and we can trial various different methods of adjusting our pumps and then simulating those in ICM in a manner when it isn't time critical ahead of there being a storm event or anything of that nature. So we already have our understanding of how the network is likely to respond in the event of a storm ahead of time. So we've got that slow learning cycle, and we can teach our neural network what it is that we're interested in and what optimal solutions there might be. So going into applying this to a specific case study, we've just been trying this on a fairly simple network. You can see that there. But we're looking at three things. We're looking at setting parameters for 5 pumps in this case, and what the optimal solution would be for those 5 pumps, taking into account that we want to minimize the flood volume itself, so we want no additional flooding over We want an optimal solution for our pumps to minimize the flooding that we see across the network. And we also want to limit our energy usage, so we don't want to be using any energy unnecessarily. And this is just an example of some of the things that you could achieve with this. This isn't necessarily the only thing that might be possible with this neural network optimizing these pumps, but these are some of the things that we could look at. So if we go back to our machine learning section, and we were talking about adjusting the pumps and simulating them using Mode Frontier and what that might look like. So in Mode Frontier, we have our workflow, and we're looking at this sort of top to bottom as we go from the top. So we've got some inputs at the top. This is our sort of pump state as we go through. We've got our ICM model, so that's all linked up through Exchange, and Mode Frontier is making changes and running various models and trying to understand what's going on. We have a set of outputs, so we're looking at flooding volume and that sort of thing as we come through. And we have our objectives we were talking about before. So we're trying to minimize the flooding volume and minimizing the energy usage, as I was saying. And we're running all of that with our optimizer here. So we're running a smart algorithm to make decisions as to the best way to minimize the flooding volume with the set of inputs that we've laid out. This is just starting off looking at one storm. We're going to look at multiple storms as we go through, but this workflow would just be for a single storm, and then we could apply the workflow many, many times for many different storms. So if we go back to our machine learning, we've adjusted our pumps, we've simulated our model, and now we can start to learn from that. So we can look at our results and apply our results to our neural network. So if we look at our results a little bit, we can see we've got a Pareto front of solutions. So we've got sort of, we can look at the flooding volume in response to this is changing all the various different pumping states, the 5 pumps there, volume flows and that sort of thing. And we can see energy usage up on the left. And what we can sort of start to see is we end up with 2 distinct regions, as it were. So we've got this linear region where for a certain amount of energy usage, we can restrict the flooding volume by a certain amount. So if we don't run the pumps at all, we end up in that region on the right where we've got lots and lots of 1,000 meter cube of flooding. If we run the pumps at their maximum, you can see we can reduce it to around about 200 meters cubed. But you can also see that we get no benefit at all from running our pumps faster and faster and faster after a certain point. So what we can sort of start to look at is this little corner here is probably the bit that we're going to be most interested in. It's sort of our optimal pump setting. We're reducing flooding volume as much as we can, but we're not using any energy unnecessarily. So we can start by training our neural network on one of those, and this graph again is just for a single storm, but we would run multiple storms, we would generate lots and lots of graphs of this. So we end up with our neural network of storms, and this got this sort of hexagonal representation, but we've applied different types. You can see different design storms on that neural network. And as we sort of go around, we can see they're linked up, they're sort of categorized. So we've got all the 5-year storms towards the bottom, 10, 20-year storms, 20, 30-year storms up on the left there. They're categorized together by sort of severity. And we've got some solutions for each of these storms linked together. So we've got our neural network. It knows about those storms. We've got the storms grouped together, as I was saying. And now we've got our neural network trained on the data we were looking at before. We can start by looking at our weather data. So we've got this pattern recognition. So we can have a look at which storm that we've trained our neural network on is most like the storm that we're experiencing now. So we've had our weather data. We're looking at that and we're going, okay, which of these previous things is most like what we have already seen? So in this case, we've got that green one in the center that we're saying it is most like, with a relatively high confidence level. So we're plotting the sort of confidence that we have in our results on there and how much each storm is like the ones that we've seen before. And we can see that that one in the center there is the best match to the incoming weather. So now we know which one it's most like. We can start using the data that we've already trained our neural network on to predict something about the storm, what we should do about the storm. So we're moving on to recommending a solution to our actual storm itself. And again, this would happen in real time. This isn't something, the training would have happened beforehand. And we can see that we have an optimal pump setting associated with that storm itself. So now that we've said, this storm is the most like that one, we can see from all our previous data from our optimizer what the best way to approach that is, and we can make that sort of recommendation. So we get a pump state for all of our 5 different pumps. This is a slightly complex graph, but we've got a state for each of our different pumps as we go through. And what we can see is if we apply, I've applied 10 different storms here just for testing to begin with, and we can apply a pattern recognition to that. So we learn, which one it's most like. And now once we know which one it's most like, we can apply our optimal settings from our previous learning, and we can go through and we can make a set of recommendations as to how our pumps should be set and what flooding we'd expect to see for each of those individual storms. So we can then go around our neural network. Now our neural network's trained and we're able to recommend solutions in real time. We can run around that neural network and integrate that with emailing our solution, so we can email our solution with the best solutions that we've identified. Sorry, I'm running a little bit short on time, but we can integrate, again, if the solution that we've come up with, we have a relatively low confidence level in, it's not like a storm that we've seen and trained on before, that's something that we can also account for. So we've got this extra set here, so we can improve our neural network if the network isn't already well represented. So we can, if we, haven't already trained our neural network on a storm that we're now seeing, we can make an initial prediction, and we can go back and retrain our neural network and gain learning from that. So the neural network becomes better prepared for the new weather as we go through. And as the longer it's in service, we become more and more prepared as we experience novel weather. That was about all I wanted to say from the technical side. John, do you want to? Thank you very much.
So hopefully that makes sense in terms of its technical nature, but if you need a kind of a simple idea, just the way in which your mobile phones work and you have voice recognition on your phone, the phone comes as standard. It's already got some trained, learned patterns of speech, but that as you use that phone more and more, it learns your voice. So as weather patterns are coming in, that's basically what we're trying to replicate here. So the highlights of what we've achieved by doing this, so we had a number of building blocks to kind of make sure that this technology could work. So we worked on a number of those building blocks. So the technology highlights is that we can, first of all, auto start an AI system from ICM Live, so we can do that. Second thing is that you can recognize storms within a database, so we've done some work on that. We can balance energy and flood optimization, so we can give optimal pump settings and keep it at good energy. We can do that in real time to avoid the limitations that we may currently have. It is a self-learning system, so we are actually capturing knowledge and using it for the future. We can still do this on high fidelity models, so we don't have to reduce the complexity of our models. And we can also validate the solution. So if the neural network has come up with a solution that doesn't have a high confidence, we can still do a one single ICM run check to make sure that is a genuine recommendation. And if it is bad, ignore it. And then the system will try and relearn from that storm. Just for the business highlights, so what does this mean for a company, water company? One, you can minimize the flood risk in real time, and while really minimizing the energy as well. So that's what it means for the company. So we're here, we've got a stand next door, so come see us if any of this has been of interest, so please do chat to us. Thank you very much.